Okay, so the Borsec-Ulam theorem is a fairly complicated theorem. What did you learn about it, or what does it say?
So it says you have a three-dimensional sphere, or any dimensional sphere, actually.
Okay, yeah, let's stick to the regular
Three-dimensional sphere.
Sphere in three dimensions that you're talking about.
So then you map it onto a two-dimensional plane.
Okay, so you have some sort of way of mapping it into two dimensions. Okay.
So then when you do that, there are going to be points that on the three-dimensional sphere they fall on top of each other in the two-dimensional mapping.
Okay, and what's special about the points that fall on top of each other?
Well, if you have, there's always going to be two antipodal points that are points that are opposite each other on the sphere that fall on top of each other.
Okay, yeah, so there's always going to be 2 points that are exactly opposite each other that end up
on top of each other
being
on the
mapped to
mapping.
the same point. Okay, yeah, it's a pretty surprising thing actually, because you would think that if you, and it's too bad we don't have a sphere laying around nearby, but you think you could pretend that's a sphere?
Yeah. So if you had like this side and then the point on this side, they would be, if you just squished the sphere flat, then they would map on top of each other.
Yeah, that's right, they would. But you would think that if this, sphere, pretend sphere,
Yeah.
was made out of like, silly putty or something, maybe you could like flatten it out or somehow move it around such that you could avoid these 2 points falling on each other. But what happens then when you do that?
You'd have another pair of points or more than that.
Some other points fall on top of each other, yeah. And did you understand the idea behind the proof?
So it was kind of, actually not really.
Not really? Okay,
So-
well, that's okay. It's complicated, right? So you look at where, sort of antipodal points lie, and then what did he do? So if this is some function f of the circle, sphere, what did he do with these antipodal points?
Well, to get from this point to the antipodal point, he just flipped the sign.
Yeah, that's right.
And then he made it to a new function that was 0.00.
Okay, yeah. How did he get to that function?
So he took a sphere and then he took a path of that around like the middle of the sphere, and then he mapped it to like a two-dimensional grid.
Okay, yeah.
And then he just moved that path farther and farther up until he got to the top, and then that mapped to one point. And then if it goes up to the top and maps to one point, that means it has to cross the origin at some point.
Yeah, you definitely have the sketch of what he did. He created a new function, g, of we'll call it on the sphere, which was f of a particular point minus f of the opposite point.
Yep.
And then he looked at this function g, and he said, well, suppose here's the origin, and suppose that the point g doesn't pass through
Not the origin.
Yeah, and g had a really interesting property that g of minus p equals minus g of p.
Yep.
And so that meant it sort of had this reflection property.
Yeah.
And so if you looked at a circle, g would kind of wind around somehow, but it would definitely include the origin inside of however it wound around. And then you took this circle and maybe you moved it up to the North Pole, and so the image would shrink down, and eventually it would sort of shrink to a point. Maybe that point was there.
Yep.
And it meant that this thing had to kind of compress in and at some point pass through the origin.
Yep.
So that was a cool argument. Okay. Let's find something, one other thing from the video to talk about. But yeah, I'm glad you got the sort of sketch of that argument. That's a pretty neat argument. Because this seems like it would be very hard to prove.
Yeah.
And it is.